So once again, good morning and welcome back. This is our second lecture in the course on fundamental principles on Catholic bioethics in the program of bioethics, the Master of Science in Bioethics here at St. Thomas University. And so beginning always with a little prayer in the name of the Father, the Son, and the Holy Spirit. O Lord, send forth your Spirit and we shall be recreated. You shall renew the face of the earth. Amen. And today being the feast of Saint Agatha, Virgin and Martyr, pray for us, intercede for us. Amen. Father, Son, Holy Spirit. Okay, so first thing, any questions or comments? Yep.
Looking at the bar, how can I tell if you're recording?
Okay, this little red dot down here, the little, they couldn't make it any smaller. And so there it is. If it's red and pulsating, then it's recording. If it's a little square, we're in trouble. It means that it's not recording. And there's no difference existentially, meaning that we all see the same and people online can hear me and see me and we can see them and everything else and hear them, but it's just not recording. So it's separate functions. So always look for the little red dot, okay? Thank you. I'm also going to turn off some lights here halfway so that we have a better vision. Let's see. Let's see. Is that too dark? Fine. All right. Not too dark, not too light. It's about halfway. Yeah. You're welcome. My pleasure. Okay. So first we want to just take a look and review a little bit briefly from the summaries. You're all on board pretty much. I get it that you're all bright students. And I'm looking here for, no, these are all the homeworks. Let me go down, scroll a little bit. Just looking for last week's presentation to summarize a little bit. We're still within the general introduction, okay? And so in my mind anyway, the issue of beginnings is very important, or origins. So we have several origins. We'll begin to look at three origins today: the origin of the universe, the origin of life on Earth, and the origin of human life, right? And this begins to clarify the issue, and that's why I'm talking about this vision of the human person, the Judeo-Christian theological anthropology. It's a mouthful, but you can see the roots. It already anchors it in a particular tradition, all right? And this will take exception to other anthropologies that are out there. Globally, we can say that are either not Judeo-Christian or non-theological. They become secular, meaning horizontal, basically just looking at the human as human without consideration for the fact that there is a God and that God reigns supreme, and somehow he has a plan, even though that plan at times may seem very, very mysterious to us or even contradictory. There's a plan somehow in the biggest of the pictures here, okay, which includes eternal life. So then also a big effort for the whole program, but particularly in this first course, the fundamental principles, is to come to an understanding and to reconcile, and more than reconcile, to actually integrate science and faith. In other words, we are on the one hand scientists, or believe and use the scientific method for inquiry, for searching and getting at the truth, thanks to Aristotle's philosophy that we do have access to the essence of things while studying and observing them and experimenting and so forth. But at the same time, we are people of faith. We have certain beliefs which are particularly Judeo-Christian, right? Monotheistic, incarnate, and so forth. So how to reconcile these so that we don't end up, sadly and tragically, like Meyer, who was, in my mind, was a brilliant mind, one of the most brilliant minds we had in biology last century, throughout the whole century, but ended up in rejecting religion, and spirituality, and the theological, basically, for a misconception that I'll bring out, which was very much part of the culture of the time, particularly the first half of up to last century, through the Middle Ages, up to last century, which is this whole issue of creationism in our field. Specifically, we're looking at nature, but also fundamentalism in the bigger picture. Okay, so fundamentalism is sadly the shortcoming here. So he was not immune, as brilliant as he was not immune to the culture of the time, which also we tend to absorb and imbue from the time we're born, practically, with our surroundings and the way we're treated even as babies, before we actually can conjure thought and put together logical processes. We're already absorbing passively, like a sponge, the culture around us, including, for example, the lifestyle of our parents or wherever we grew up the first few years, even before we're exposed to a school, which may have been like, say, preschool, you know, I have pre-K 3, pre-K2, pre-K3, pre-K4, and then kinder. And so basically at about 2 or 3 years of age, the kid is already being socializing, right, with other kids who may or may not have their same value system at home. But even that value system is never exempt from the culture around us. And our culture, more and more over the decades, has become more and more secular, humanistic, and what I call horizontal, you know, missing many times the vertical dimension. In other words, the connection with God, spirituality, religious practice of any sort. All right, so trying to reconcile this, and beyond reconciling, actually integrating. My hope is that by the end of this course, right, around May, you will be convinced, if you're not yet, that actually science and faith complement each other by giving us the fuller, bigger picture, and kind of a mechanism. In a way, science or nature will give us a mechanism of how God is actually working in our lives, in our world, and in our universe. Okay, so we will be able to be people of faith who are also scientists and not be schizophrenic. Please. Yep. Yeah. Sorry, if you speak a little loud so that it will be picked up.
I just wanted to pose a question
Yep.
on kind of the topic that you're discussing right now, based on Meyer's upbringing.
Yes.
In evangelical, Episcopalian,
Right.
versus Mendel's upbringing as Christian Catholic.
Yes.
Which
Sorry, you're talking about Meyer or Darwin?
I'm sorry.
Yeah, contemporaries.
Darwin
And Mendel.
Meyer,
And Mendel.
well, yes, Mendel and
But then Meyer for the
Darwin, but
synthesis.
I'm synthesizing Meyer into Darwin.
Okay,
I'm
okay.
sorry. Yes, you're right. I don't know the upbringing of Meyer, but I thought that
Right.
they may have
Just that they're a
similar
century
background.
apart, but basically he was inheriting that.
So I'm just wondering if that issue with fundamentalism comes more from the, I would say, Protestant tradition
Yeah.
than from the Catholic tradition, although the Catholic was very fundamental back in the Middle Ages. But I think by
Yes.
Mendel's time, it would probably had evolved because of the university system, as you had talked about.
Yeah.
A broader worldview, which maybe was a little bit more ecumenical, maybe had the ability to synthesize and integrate a lot of the science and faith, especially if you look at from that kind of Thomistic type approaches. versus the fundamental, which was sola scriptura, where you could only believe if it was in the Bible, and if the Bible said it, that's the only faith that you were allowed or you would interpret. And maybe what was actually happening was that maybe Darwin and Mayer, which were not accepting of, I would say, the Catholic or vertical perspective, were actually rejecting their own faith or their own Protestant backgrounds. Because they could only see it from that sola scriptura perspective.
Right. So the short answer is yes and no. It's like life. It's complicated. Okay. There's several different confluences of rivulets that feed into streams that feed into the bigger river. All right. I also want to mention, because you raised the point of fundamentalism and sola scriptura and literal interpretation of sacred scripture, lest they, I mean, there are passages galore, both in the Old Testament and New Testament, that if any part of this sentence or the phrase or the statement is denied, then one is anathema, one is thrown out. Even Jesus himself mentions not even a tilde, an iota, right, like a comma of the law would be changed and so forth. So there are strong passages there calling to faithfulness. We have advanced in that. When I say we, I mean Catholic theology has advanced quite deeply, frankly. But you're right, it's a cultural influence. And sometimes this cultural influence is subconscious. That's why I was making reference to the early years, because we absorb it. And by the time we get to the issue of faith or religion or spirituality, which will come maybe for when we start preparing for maybe First Holy Communion or something like that, we already have an underlying cultural system and value system that has come from our surrounding, which is not necessarily Judeo-Christian. Okay, and so in a sense, we in the Catholic Church are always playing catch up. I think Christina could speak to that issue, being a catechist at a parish, right? And having to deal, a religious education, having to deal with that catching up. Because now we have to become like apologists in trying to present the reasons for why our faith, you know, because culture already got the first grounding. But I also want to pick up on fundamentalism, that it's not exclusive to religious fundamentalism, okay? There's also what I call scientific fundamentalism, which is that only empirical science counts, only that which can be measured. And I think Einstein, in a sense, fell into that, only that which can be measured, what is the proof, can be measured, right? And that's their religion. There's a secular fundamentalism also, which is only that which is humanistic and horizontal, and absolutely no reference to the supernatural or the transcendental, because for them, for the secular humanists, that is an opinion. Okay, and they leave it at the level of opinion, which is 100% subjective. So they're all different types of fundamentalism. There is also a Catholic fundamentalism, which a number of us have encountered over the years and the decades. It's kind of a fideism where some people need all these crutches to hold them into the faith, and they tend to become very devotional, right? To the point that Mary becomes a bigger goddess than Jesus Christ. And it's almost like through Jesus to Mary instead of through Mary to Jesus. Again, to me, one way or another, it's because we just haven't thought sufficiently and pondered and reflected and being quiet in the presence of mystery sufficiently. On the one hand, because it's intimidating. On the other hand, also because it just burns more ATPs. It takes more energy to reflect and to think. And so I see it at the parish all the time. Father, don't worry about it. Just give me the answer. Just, should I do it or not? You know, should I do IVF or not? Don't explain to me what is involved or all the manipulation of the embryos. Just tell me, should I do it or not? Just give me the answer. And I don't want to think for them. I'll help them think, but they need to own their own answers, right? And so thinking is always harder than non-thinking. And that's because, see, nature is economic, right? If something works in nature, nature will not reinvent it. It will just keep doing the same thing, like DNA, for example. It worked for some species early on, so it just kept doing DNA for the inheritance molecule over 4 billion years, 10 to the ninth. Okay, so obviously DNA works as a universal molecule of inheritance. Don't fix it. Then, but lost the thought. Yeah, if it works, don't fix it. So nature is economic. I translate that for the human. The mind is lazy. We'd rather not think than think. And that's what happens when, with my undergraduates, they're doing, for example, some math or some physics or some chemistry. In 1 hour of studying the book, they're tired and they haven't moved the muscle, you know, but they've been thinking. And so they're tired. They're literally, their eyes are closing, their eyelids are closing because they've been burning more ATPs than watching TV, which is very passive for the same hour. And then they say, well, how come I didn't lose any weight if I was, well, because you're tapping into the active glucose, not into the glycogen, which is the storage. You want to lose the weight, go out and run for an hour, do the physical exercise. The mental exercise will get you tired without burning the glycogen, the fat. Okay, we'll get more into these issues, and I'll even give you some chemistry to go along the way to prove, you know, what I'm talking about. But you get the picture. We do need to ponder and reflect, and then also pray. In other words, ask for God's guidance and mercy and the inspiration of the Holy Spirit, because certainly we are big time fallible, right? And therefore we need that guidance. So it's a process. It's a process, and we believe that the Lord does not abandon us in this process. Also because there are certain things that God cannot be. It's interesting how God is omnipotent and omniscient and all these omnis, you know, we put restrictions on him, at least from our organic perspective of the thought process. He cannot be cruel. He cannot contradict himself. All right. And so if Jesus says, I am the way, the truth, and the life, we can put those with capital letters. The truth is right in there, and that's our quest. That's our lifelong quest, really. And so we do have access. It's not going to tell us you need to search for the truth, but you know what? You don't have access to the truth. That'll be utterly cruel, right? All right. So yes, the origins, that is like two-phase origin of the species as a whole. I'm talking about the human species, and that's why I've gotten into a definition of species and an organic functional definition of species, which is the biological definition. And then also ontogenetically, meaning at the level of the individual, because obviously you can tell from in today's society, you know, one of the bombshells, one of the cultural bombshells is, when does human life begin? And I mean, I've been involved in pro-life way before the priesthood, when I got my bachelor's in biology from FIU, a secular university, back in '73, which coincided with the Roe v. Wade decision of legalizing abortion up until the 9th month throughout the whole United States. Okay, talk about schizophrenia. And just from a scientific perspective, I say, how can it be? Everything that I've been learning about human embryology for the past 4 years at a secular institution, you know, all of a sudden it's out the window, and we can kill the unborn with impunity up until the 9th month. Something's got to be wrong here. So that's why I've been involved in pro-life for so long. But to me, to this day, it's still a puzzle why some people question when human life begins, just from the biological perspective. It's not a religious issue. I know that the opposition likes to frame it as a Catholic issue. Okay, you want to see a very interesting movie? It's Roe v. Wade, precisely. Roe v. Wade. It's an actual movie, came out a few years ago, just recently, and it's a whole recap. It's actually Bernard Nathanson, the largest abortionist in the United States. When I think he said one time he had clinics throughout the whole U.S., abortion clinics, and he was part of the movement to legalize it. He said, it's in Netflix. Yeah. Roe v. Wade. he said personally, when I got to do 2,000 abortions, I stopped counting, okay? And he had staff, which was in the hundreds, if not thousands, throughout the United States, doing this abortion machinery. Anyway, he has his conversion experience, but it's always framed oh, that's a Catholic issue. So here are the Catholics acting up again, right? But it's not, it's a human issue because humanists, secular humanists, it is, you know, it's an objective thing. We'll see it next semester, as a matter of fact, throughout the summer in the course at the beginning of human life and all the ramifications, the bioethical ramifications of yay or nay. You know, if life begins at fertilization, yay or nay will make a big difference, the big divide with regards to the bioethical analysis, right? So we need to be scientists. We need to provide the scientific evidence, hardcore objective evidence that does not depend on my opinion. Because right now, looking at the window, the sky is blue and I may think it's orange, you know, but unless I have a weird definition of orange, it's not orange for the rest of the people who are looking at the sky. It's blue. We can discuss the different shades of blue, but we cannot say orange versus blue, right? Anyway, kind of getting ahead of myself and going tangentially. Yeah.
It was incredible that this
Mm-hmm.
guy, Catholic, he was Jewish.
Yes.
And at the end, he convinced that
Yeah.
Catholic has the truth, the sense of the human life, respect, and all this.
Exactly. So he landed. He actually did.
And morally and religious.
Exactly. He did a two-step, kind of a three-step, because he was, like you mentioned, brought up Jewish, but then it was cultural for him. It wasn't really, he was a humanist, you know, because the Jews, the real Jew truly believes in God and monotheism, and it's a fear of God, and that we are created in its image and so forth. And there are plenty of references in the Old Testament about before I formed you in your mother's womb, I dedicated you and so forth, okay? But then not only did he become pro-life, which was just spectacular to realize and he realized it by the evidence, in other words, by seeing an actual sonogram, not by belief, but by evidence. And then he took the final step on landing into Catholicism with all due respect, the fullness of the truth. Right? So quite spectacular. It reminds me of St. Augustine, how he was a wild kid, and before he became a saint, he was a little devil out there, but eventually St. Augustine, the son of St. Monica, all right, many centuries earlier. Okay, so anyway, diverging a little bit, but you get the whole issue of origins and the fact that we want to be true also to both to science and to religion. We want to be true to nature as we see it, including our human nature, and we also want to be true to the supernatural, which is the whole issue of the existence of God and the consequences of that. Okay. All right. So I don't know, any other questions or comments? Yeah, this was like the introduction. So just scanning through the, scrolling through the outline of the first lecture. And you can see there's a little bit of overlap. We'll discuss Bayer toward the end of the lecture today, probably in the second half. Is specifically chapter 1, okay? But, all right, anything else before going forward a little more deeply into today's second round? So I want to talk about the issue of worlds in quotation, all right? These three worlds that I talk about that we live in simultaneously. Also back to origins, specifically three origins, and a fourth one there, the second origin split into two parts. Then, I'm sorry, the first origin split into two parts. Then the four fundamental forces in nature. So we'll go a little bit back and forth. We'll do mostly some physics today, some biochemistry, and some anthropology, especially the second half. Right. Yeah, it's still recording. I hope the little red button's still there. Yeah. Thanks. Okay, so we'll look at the four fundamental forces from the physical perspective. We'll look at the four organic molecules from the biochemical perspective that allow for the possibility of life. Then we'll also back into a little bit of climatology and look at the primitive atmosphere and talk about the Earth as it was forming. Then back to the review, the definition of species and why it's important and meaningful. Then applying it to the human species at the level of genus. See, also that's why I gave you the Linnaean classification, which is still standing today. Interesting, man from the 1700s and his paradigm is still being used more than 300 centuries, 300 years later. All right. So the level of genus, which is kind of our last name, biologically speaking, Homo, how we share that with other species of Homo who are all extinct, which are all extinct. Okay, so we're the only Homo species living today, but we have plenty of fossil record evidence of other Homo species. And the big question, of course, theologically is, did they have a soul or not, right? Were they destined for eternal life? So that gets to the whole phylogenetics issue. And then finally, modern history of science from Meyer's perspective and a little critique of him there. So without further ado, the three worlds that I sustain, we live simultaneously, but we're really only aware of what I call the middle world, all right, or the normal macroscopic world. This has to do a little bit with our senses. And again, external senses, the five traditional external senses for which we have neuronal termini at the cover of our body, basically the skin. So what do we have? Just to review very briefly and to bring everyone on board from different academic backgrounds. The five senses, traditionally, the five external senses are, so vision, the most important, on average, they say that at least 90–95% of our information comes through our eyes, okay? And second to that, typically, would be the hearing, right? Then we have them all on the head, by the way, and then just one from the head down, from the neck down. But there's obviously smell, also associated with the others. Very much smell and taste are very closely associated, right? And finally, tact or touch, which subdivides into several others, like touch will be pressure sensing or pain or hot and cold, which are also distinct, so we can feel hot and cold at the same time, etc. So these are the external senses. And why are they called external? I'm just kind of thinking out loud with you, right? They're called external for two reasons. One, because the stimulus comes from the outside of our body, which again, by way of biological integrity, we can consider the skin holds us together, right? And defines our integrity, what is self and what is non-self. The boundary is the skin. And that's also important because we are not, even though we are immersed in an environment, and like Ortega and Gasset used to say, I am myself and my circumstances, yes, fine. But there's also a specific limit to myself, which is the skin, all right? And so I am not part of the wall, and the rest of the environment is not part of me in a biological sense. I have an integrity to myself that is defined, bound up by my skin, otherwise known as the integumentary system, and it's at the level of system. We'll talk about that other hierarchy of cell, tissue, organ, system, organism. Okay, I'll talk about other hierarchy next semester a little more deeply when we get into biology. Basically, yeah, sorry, Christina.
I'm sorry. Are they part of the microscopic of the normal microscopic? I got confused a little bit there.
Okay, here I'm talking about the normal macroscopic. That's what I'm talking about right now. Okay, the middle, what I call the middle world, the middle world.
Thank you.
The one, so we live in these three simultaneously, but we're not generally aware of the microscopic or the super macroscopic on a daily basis, okay? We move in these three worlds simultaneously, but we're only aware normally, even subconsciously, of the normal macroscopic world. And so I start with the senses because those are the stimuli that we receive from the moment we wake up in the morning until we finally fall asleep at night. Every conscious moment of our lives is being bombarded by stimuli, most of which we have to reject, otherwise we go in overload, all right? And that happens subconsciously. There's all kinds, there's a temperature right now in this room, there's a particular atmospheric pressure, et cetera. We just kind of take it for granted and we're comfortable enough. Unless it gets really hot or really cold, we don't pay attention. We're not aware of all these other stimuli that are hitting our senses constantly, all right? Unless it's Father Chaffee talking away about something. So we're aware of that. The hearing right now on the site are the ones that are being highlighted and stimulated. They're also external because there is, in contrast, an internal sense, which goes by various names, but the one that I'm most familiar with, I think, is the kinesthetic sense. I don't know if you've ever heard of the kinesthetic sense. Which is an internal sense, right? It's an internal sense that has to do with motion also, but it kind of integrates the other senses, the external senses of our body, and kind of makes sense of what we are perceiving. And one time I had the crazy idea to ask the doctor, the medical doctor that is, why do I have the toes? Because I keep knocking my little toe with the bedpost, with the wheels, the metal wheels at the end of the bed, at the corner of the bed, and I keep jamming it and breaking it. Why do we have the toes? Why can't we just get rid of the toes? It's, oh no, that's horrible. We can't get rid of the toes because it gives us fine movement on the stepping. We can step grossly, right, and put a foot in front of the other and keep walking or running or jogging even backwards, whatever we're doing. But the toe picks up the fine detail down to the millimeter. And it otherwise, without the toes, we'd just be walking crazy, sideways, bouncing. We wouldn't really have a real sense on the fine tuning of moving forward, sideways, speed, and so forth. So we need the toes. Right? That's the kinesthetic sense is integrating the others, and it's kind of making sense of the stimuli or not. Okay. Right. So anyway, that's the world we normally move move about. But there's also the microscopic world, which by definition is beyond the range of sight. And that's also another thing. Our senses, our external senses, have a range, and but that range continues outside of what we can detect, and it's still there and real. For example, you've heard of the dog whistle, right? The dog whistle, the dogs hear it, but we don't hear it because it's a pitch that is so high that it's beyond what we can pick up. All right. There are many sound waves and other kinds of waves that we don't hear, thanks be to God. Otherwise, we go crazy with the cacophony and just the chaos of noise that if we start picking up stuff. For example, right now in this room, there are all kinds of waves going through here that we just don't pick up, thanks be to God. So let's say we have a radio, okay? And we turn on the radio, all of a sudden, depending on the dial, depending on the frequency, we can pick up music, talk, etc. All right? All those waves are going through the room. It's not that that talk show or that song started when I turned on the radio. No, it's been going on and it's going right through this room right now. And unless we tune into that particular frequency, we can't hear it. Again, thanks be to God. Not only normal radio stuff that is going through out to the public, but also confidential information, classified. If I pull out my cell phone, I can do banking on my app in my cell phone, and it's not that the bank opened just when I opened this thing and the bank is inside my cell phone. No, those are waves somehow that are going through this room. They're frequencies that my app in my cell phone picks up, and I can actually do banking in a secure site, right? And so forth. There's even classified information that's going on. So if we were military and have one of those dedicated laptops that are military and so forth, we can encode and decode and recode and all that. That's going on through this very room right now. Okay. And so again, thanks be to God that we don't pick up all that in the normal macroscopic world, in the mid world. Otherwise, we just go crazy. But it's there. It exists. Objectively, really, whether I believe it or not, whether I understand it or not, whether I like it or not, we are being literally bombarded by all these waves. Electromagnetism, for example. We're exposed to the gravity of the Earth and the electromagnetic waves that are going through. And it doesn't really affect our body very much unless we actually get into the microwave, then that's a different story. Then, okay, so there's a microscopic world that also goes by layers, if you will. We can look at the back of our hand, for example, and the smallest we can see, if we kind of focus in with or without eyeglasses, all right, look at the back of our hands, we can see the hair, and then we can see the smallest we can see is actually tissue, just the skin tissue. We cannot see the individual cells, but we know that that tissue, we know from science that that tissue is made up of cells, epidermal cells, which is really quite complex. And even the hairs, the individual hairs, each one has a little tiny muscle that is connected and a gland and so forth. And that muscle, that's where we get goosebump. That muscle contracts and forms the goosebump, all right? It's called the erector pilus. One pilus, several pili. It's a reference to the hair. So it's amazing that each individual hair in our body, all over our body, that makes us mammals, has a muscle attached to it, which is microscopic, but it's real and it's there, okay? So, and that's kind of just with what we call a light microscope, which magnifies into the hundreds, maybe 1,000 times. Then we can go deeper into the microscopic world with more sophisticated microscopes that can see in the thousands to hundreds of thousands. Typically, there are a couple of types of electron microscopes, transmission electron microscope and scanning electron microscopes. They are so powerful that they don't even use physical lenses. They use a magnetic field for a lens. A magnetic field is the lens, all right? When I was at Purdue, the whole floor, one of the science buildings, we have several science buildings in Purdue. It's a huge, it's a big tech, Polytech university, 50,000 students. Anyway, the science building, the Lilly science building, as in Eli Lilly from the pharmaceutical, who donated several $1 million to build it, is 3 stories above ground and 4 stories below ground. Because there's a lot of dirt in the Midwest, okay? And the bottom floor, the -4, okay, downstairs, was all the labs with electron microscopes, because that's the place that vibrates the least. And they're trying to keep that as least vibration as possible, because any tiny little vibration that we don't feel, the electron microscope can discombobulate because it's so sensitive, so extremely sensitive. But they use magnetic fields instead of lenses to magnify. But we've done. This is at Purdue in Indiana, Purdue University. Yeah, that's where I got my genetics degree. So it was fascinating going down there and watching all these equipment. And even that is kind of outdated now. There are photon microscopes and microscopes that can actually see molecules. All right, so macromolecules, DNA has been photographed and so forth. So we're into the level of maybe 1 million magnification, 1 million times magnification. It's just fascinating. That's in the microscopic world. And we know from scientific evidence that beyond the molecules, of course, molecules are formed by atoms, which is a stable unit of matter. We'll get there a little further on. but even atoms are formed by subatomic particles. The classical three are protons, neutrons, and electrons. But even those subatomic particles are made up of smaller fragments, which are generally called quarks. And even the quarks now is thought to be made up of the smallest thing that has been found empirically yet, which I think is called the quantum foam. Okay, so it starts getting a little esoteric, the little sci-fi, at least for my mind, but the quantum foam apparently is what is making up the quarks, because of different types of quarks, including that Higgs boson particle that was found a few years ago at CERN. That's the European Nuclear Research Institute. I had an opportunity to visit one time between Switzerland and France. They have the hadron, they have a collider, hadron collider of particles. Fascinating. Okay, so when we back out now from the macroscopic and through our normal world, okay, of the senses, we go into the super macroscopic. Sorry.
So you had said that there were 3 levels of microscopic.
No, several layers, several levels or
Okay.
layers. Yeah, just it keeps going deeper and deeper.
And they're defined by magnification.
Basically, yes, by magnification. So we're into space, but then I'm going to make the relationship space-time. Actually, we need to talk about the space-time continuum, which is the 4th dimension, space-time continuum. All right, so I kind of the three classical dimensions of space are what we call Euclidean geometry, which is depth, height, and height, depth, and width, right? 3-dimensional, X, Y, and Z, 3-dimensional graph, Cartesian, not Euclidean, sorry, Cartesian, what we call Cartesian space. Then the 4th dimension is time. But actually, through the work of Einstein and the other theoretical physicists and quantum physics and so forth, we have actually the space-time continuum. It's just that the time factor, again, we're not consciously aware of, but it's constantly happening. All right, so we're not at the same place that we were when we began the lecture. We are locally here in this room, and each one of you virtually in your own room, same local space, Cartesian, but not with respect to the rotation of the Earth, for example. We're already at a different location with respect to the rotation. That's just within the Earth itself. Then add to that the translation of the Earth around the sun. That's a second frame of reference, all right? And even the sun, the solar system as a whole, moving within the Milky Way galaxy. And then that galaxy within the universe, in the expanding universe, by acceleration, not just velocity, but actual acceleration. So we have at least 4 layers of displacement of different places at every particular time, right? There is the displacement beyond the local to the world. There is then the world, Earth, planet Earth, around the solar system, the planetary system. Then there is a solar system within the Milky Way galaxy, and then our galaxy as a whole within the expanding universe. Interesting. So we end up with a more realistic view is a space-time continuum that the quantum physics are telling us today. So that segues into the super macroscopic world. And just very briefly, when we look at the super macroscopic, I'm talking about distances and events that is so large, and even time that is so large. And I'm going to pick up on the time, particularly when we come back to planet Earth, what we call geologic time, which is typically hundreds of thousands or millions of years. All right, geologic time, very, very slow process. But back to space and super macroscopic. Just last night, right around 8 p.m. or so, I looked out the window and it seemed to me that it was a fairly clear night. For the first time, I noticed in recent days, I love to look at the moon and the different phases of the moon and so forth. And it turns out that the moon was setting, first of all, it was a little sliver, it's a crescent moon, and it was setting early. So it was a moonless night from about maybe 9 or 10 p.m. forward. And it seemed to be fairly clear to me, meaning devoid of some cloud or humidity. And what happens with cloud and humidity is that it picks up the reflection of the lights, the city lights, and then it bounces it back. So it makes for fuzziness, and we cannot see the stars too well. All right, that's a typical phenomenon of urban areas, that we cannot see the stars generally too well because there's a lot of reflection at night of either the cloud cover or the humidity. But last night seemed to be fairly clear still, the remnants of the cold front that we had that sucks out a lot of the humidity. So anyway, by the time I got finished grading and reviewing and emailing your summaries and so forth, it was about 1 a.m. So I went out, I walked into the parking lot of the church, which is fairly dark. I looked up and I could see quite a few stars. And I thought that I could see a very faint glare of the Milky Way, which generally appear. I've seen the Milky Way before up in mountain ranges in Colorado and in Spain, where there's literally no city lights around for miles and miles, and it's a very dark, very black sky at night, and you can see clearly this. Well, it's just a band glare of stars, some of which are distinct and many of which are not. I don't know why it's in plurals. Milky Way. Yeah, something like that. All right, I've seen something like that, almost as dramatic as this. That's the Milky Way, which the other solar systems that are within our galaxy, we're kind of looking into, we're kind of standing, well, we're at the periphery anyway. Our solar system is on the periphery of the Milky Way, but it's looking in horizontally, let's say, into the thickness of the Milky Way, all right, talking in lay terms, and you see stuff like that, right? And then these other objects, stars, are outside of the Milky Way, or they can be closer to us, forming kind of a canopy, if you will. It's hard to tell, at least just from plain sight. But anyway, later, and I started rotating like this on a single spot, just rotating around, and then later I was convinced I know what I was looking at. It's actually some faint cloud that was there. So it was not a real fish, it was a plastic fish. It was very real. But I could see distinct stars quite a bit. But the stars that I was looking at are really in quotation, because I was not looking at real stars, most of them, most of the dots, the twinkling stars that we see at night on a clear night are not real stars, all right? Because a star is like the sun. It is a ball of fire, essentially a humongous ball of hydrogen that is on fire, okay? And so we can classify globally the stars, the little dots at night are twinkling, into two groups, the big ones and the little ones, okay? The kind of brighter dots, or the little tiny pin dots, okay? And basically the brighter dots are actually planets in our solar system, the large, the mega planets, Jupiter, Saturn, those are the two main ones. And what happens is, so those are opaque bodies. They're not luminous bodies. The sun is a luminous body, it emits light, but we, the Earth, are opaque body. We don't emit light, we reflect light from the sun. The moon is an opaque body. But how can we see the moon at night? Because it's reflecting, part of the light that is hitting it is reflecting, and we can see it on the Earth, okay? So the same with those other planets in our solar system, it is the light that they are reflecting toward us that we see. And those are the brighter, the bigger dots. The little dots are not a single star, but they're actually whole constellations. They're actually galaxies. It's just that they're so incredibly far away that they seem to be, they look to us, to the naked eye, as a single dot. But if we were to take a rocket and go lightning speed toward them, they would start just
Expanding.
what's the word?
Expanding.
Expanding and showing their individual nature, their individual identity as individual stars or solar systems, right? There's that old little experiment that you can do, that one can do if you have like a hallway or something like that, or even outside in the parking lot at night. Two people, one person is observing, the other person is walking backwards with two flashlights that are turned on, and he can hold, or the person can hold, well, don't want to walk backwards, you can walk forward, but just hold the flashlight. The person who's walking away from the observer will hold two flashlights facing backwards on their hands extended out, all right? And if the person is close enough, you see two lights. We, the observer, will see two lights. But as the person walks further and further down the street, a few blocks away, those two lights are going to start converging and coming closer and closer just from the perspective. It's called punto de fuga. It's in English, what is it called? Vanishing point. The vanishing point is an optical illusion, like the train tracks. You stand on the train tracks and they seem to meet, they seem to converge out in the infinite somewhere at the horizon. But you know, for the train tracks to actually be functional and not derail the train, those tracks need to remain parallel all the time. But they seem to be joining at the horizon, which is called the, what did I say? Punto de fuga? The
Vanishing point.
vanishing point, exactly, all right? So you get the same effect with light at night with two flashlights that will eventually, if the other fellow goes far enough, they seem to be, those two flashlights converge. They're not converging because the fellow still has his or her arms extended out. But to us, it's the vanishing point thing. Well, the same when we look at the stars. Those little dots are actually entire galaxies which contain millions of solar systems like ours, all right? And each one of those solar systems potentially could have dozens of planets around them. Mm-hmm. And so the possibility of having liquid water in any one of those, which is a very narrow temperature range from 0 to 100 centigrade, which allows for the possibility of organic life as we know it here on Earth, is really quite spectacular. Okay? Quite spectacular and quite probable, just simply because of the sheer number of these solar systems and the potential for planetary systems to be out there at just the right distance from their sun to have the temperature for the possibility of liquid water on the surface. All right. So anyway, you get the three worlds. Christina.
I just wanted to share, because I love looking to the sky and all those things that happen, that during these mornings, I get out of 6 o'clock in the morning to 6:20. And if you look to the southeast, there's something absolutely beautiful these mornings. And I think it's a planet, but it's bright and so huge. And it's really the first time that I have seen it. And I just wonder what it is. So you can help me find that, I will appreciate it.
Yeah, super. Exactly. So these are what I call the wow moments, right? When we look at the sunrise, or when we look at the Milky Way or sunset, we go, wow. And so it's interesting also because some people will say, well, look at this sunrise. How can there not be a God, right? And then some other people will say, wow, look, I can explain to you that sunrise to the T, down to the millesimal movement of the planetary motions of the elliptical and the perihelion and all that, and the precession of the perihelion by the astronomers. And how can there be a God if we can just explain it down to the detail? And so we have a little phrase for those who believe, no proof is necessary. And for those who don't believe, no proof is sufficient. So we keep chasing each other's tail around the same old tree. Anyway, going forward. Well, it's just an exercise. Yeah. So the three big origins that we'll talk about one way or another. Of course, the one we're most interested in is the human origin. on the phylogenetics part in this course. But we got the origin of the universe about 13.5 billion years ago, more or less. We'll cover it more when we get into the course of environmental bioethics, which will be in the fall. All right. No, sorry. Yes, fall. But in environmental bioethics, we'll look at more detail in the origin of the universe, and within the origin of the universe, the origin of our planetary system, which is about 4.5 billion years ago, 4.5 billion years, get to the 9th. And then within our planet, the origin of life, more or less about 4 billion years ago. So once the Earth cooled enough to have a crust and to have liquid water, life sprung. About 4 billion years, about 4 billion years, 3.8.
Universe, you said 13.5.
Okay, so again, the numbers, I have the numbers further down. I'm just getting ahead of myself. So don't worry about the numbers now, you'll see them. Then the origin of humans within the origin of life at some point, but late, very late. We're kind of the latest species and most advanced that has arisen, evolutionarily speaking. So three big origins. The one on the universe we'll look at in more detail in the fall, and these two we'll look at in this course. Here the numbers, by the numbers. So the universe around almost 14 billion years ago, that's 10 to the 9th, all right? The Earth, the planetary system, our planet, and all the other 4 inner planets and the 4 outer planets and so forth, about 4.5 billion years ago, BYA, billion years ago. Then there's a little exercise here. I'm not going to bother with it, but basically just to get a feel for how much is a million, because, you know, we're throwing around these numbers as if they were just a glass of water, okay, that we drink without thinking about it. But a million is a huge amount. One time I was hearing a talk from one of our, first he was a county commissioner, who then became a state representative, and now he's in Congress, okay? And he was talking about the budgets that he will deal with, and he said, well, at the county level, I deal with millions of dollars of budget, and then at the state level, I deal with billions of dollars, and now in Congress, we deal with trillion-dollar budgets. I say, woo, orders of magnitude 1,000 times over, just like that, in one sentence. So if you want to do just a simple exercise of how long it takes to count to 1 million, to count to 1 million sequentially, let's say that we count just a number a second, you know, 1 digit a second, so that in 1 minute, we would count 60. And in 1 hour, 300 seconds. You do that division, counting every second, one number, continuously, day and night, 24/7, without breaks. It takes between 4 and 5 hours just to count to 1 million, 4 or 5 hours continuously. That's with no breaks. And also keep in mind that as the numbers increase, they're just getting bigger and bigger to say, right? 300,000 to exactly. So it takes longer and longer, certainly more than a second to say those huge numbers. But it's a huge thing. When we extend that to 1 billion, you know, it takes several days. It's several days just counting around the clock to get to 1 billion. And yet, astronomically, the time and the distance in astronomy is measured in the billions. And geologic time on planet Earth, typically the standard unit is 1 million. So even 100,000 years is small compared to geologic time. I also say this because we're going to pick up on this in climate change. So climate is measured in terms of geologic time. And we just haven't had the equipment and the time, literally, to measure significant change climatologically. Weather is a different story. Weather is what's happening every day. But climate is long-term, okay? Even so, there is some evidence, mostly indirect evidence, that we are heading toward global warming in the current scenario. All right, another one, just grabbing from here and there, is the famous Einsteinian equation of how a conversion of matter and energy. So this formula is very important because it's a tremendous insight that is called the matter-energy equivalence. In other words, for the universe as a whole, there is a discrete amount of matter/energy. But at any one time and place, that matter/energy is being interconverted back and forth. All right. And the conversion key happens to be a constant C. I mean, talk about humility, right? This is small, lowercase c stands for the fastest thing of the universe that we know of, which is the speed of light, 300,000 kilometers per second. So just to have a perspective, let's translate that into miles and give it the benefit. So a mile is 1.6 kilometers, but let's say it's 2 kilometers. So let's say it's 100,000 miles. That 300,000 kilometers is 100,000 miles. We give it the benefit of the doubt. We have a photon, we have a particle of light here right now, holding it between our fingers, and we release it. In 1 second, which is 101, or in football, 1 Mississippi, right? Remember the Mississippi for the tag football? All right. So in 1 second, that photon is 100,000 miles away. 100,000 miles away in 1 second. And in 2 seconds, it's 200,000 miles away. And it keeps going. But its speed is velocity. It's not acceleration. All right. So it's a constant speed, and it's the largest speed that we know of on Earth. So that's the limit. That's the upper boundary. In other words, as far as we can tell so far with instruments, nothing goes faster than the speed of light. Not even Superman. But you notice that in the formula, the constant c, the speed of light, which is a velocity and not an acceleration. A velocity is when we are on I-95 or the Palmetto Expressway or I-75, we are at, let's say, 65 miles an hour. Yes, and we set up the automatic thing, and it's speed, cruise control. That's velocity, constant speed in a straight line. But acceleration is either increase or decrease, which is deceleration. It's a negative acceleration, right? When I step on the accelerator or the brake, I'm either accelerating or decelerating, a negative acceleration. That's no longer constant speed. That's now an acceleration or deceleration. Or a constant speed in a curve also becomes an acceleration by definition. Constant speed in a curve. So instead of going straight across the Everglades, now I have to negotiate a curve somewhere around Mobile, Alabama. And so now my car is actually accelerating, even though I'm trying to maintain the constant speed around that. But that curvature makes for an acceleration. I have to actually press on the accelerator to maintain a constant speed around a curve. All right, so you notice that this is an acceleration. It's a speed of light squared, which is hypothetical. Because if the speed of light is the fastest thing on Earth, how can we accelerate the speed of light? All right, so it's hypothetical, but it works. It's theoretical, but it works. In other words, this mass energy equivalency works because, and the proof is the nuclear bomb, and also nuclear energy in general. So nuclearity, right? Nuclear physics, a nuclear reactor can either give us a nuclear bomb or can give us a nuclear station that can light up an entire city, like Turkey Point down south for us in Dade County. Okay, so the mass energy equivalent works, and the proof is just nuclear reactors, etc. But it's very interesting that this gives us insight into the whole of the matter/energy component of the universe. All right, now this segues into the 4 fundamental forces, which I think this is a little old because nuclear physicists already begun to combine. I think, yeah, I think it's electromagnetism and gravity. Somehow there's a formula for equating the two. But anyway, classically, these are still what we call the four fundamental forces, right? Which are the first two, the strong force and the weak force, are precisely at the atomic level, which is a stable unit of matter, is the atom. And electromagnetism and gravity are pretty much at the macroscopic world, at the astronomic world, okay, at the universal level. So these two forces are also known as attractions together. Strong and weak force are attractions. And these two, electromagnetism and gravity, are known as fields in the language. So the strong and the weak force are known together as attractions. And you'll see in a minute, I'll give you the example. And then the electromagnetism and gravity are known as fields together. So we can say two clusters of fundamental forces, the attractions and the fields. All right, we're all subject to them, and it's keeping the universe together, but they're there. So the strong and the weak force in the atom is what is holding the atom together, actually, so that it is a stable unit of matter, the stable unit of matter, and the strong force is what's keeping the protons together in the nucleus. So we look at atomic theory. Right? The classical, what is known as the standard model, Bohr's model, the standard model of a nucleus, and then orbits around that nucleus. The orbit is the electron cloud, is known as the electron cloud, because there is the possibility, the probability that it will be at any one point in any one time, but it forms a cloud. But the nucleus is made up of particles that do have significant mass. The electron doesn't have a significant mass. It has mass, but not significant mass. What's more important about the electron is the charge, which is negative. The nucleus, on the other hand, has a proton, which is positive. So that's, you start there, a proton positive charge. And the electron negative, therefore, it's going to orbit around the proton. But then there's another subatomic particle in the nucleus that doesn't have a charge or has a neutral charge, neither positive nor negative, and that's the neutron. So neutron, neutral charge. But it does have significant mass, so it adds to the mass of the atom. And that's what makes the isotopes on the different elements. So the number of protons make for the different elements, starting with one proton, hydrogen, and that's the number that is above the letter. I'm pointing here in the classroom at the periodic table of the elements on the wall. You can look up periodic table of the elements. It's just all over the place since we were little kids in elementary school, et cetera, et cetera, et cetera. And the little number above the letter representing each element, about 100 of them. The number above is the number of protons. Okay, so that's mass, which in vulgar, we talk about weight. When we weigh ourselves on the scale, we're not really weighing ourselves, we're massing ourselves. If we wanted to have the weight, our actual real weight, we'd have to multiply that times the gravitational pull, which is 9.8. No, sorry, let me get out of the numbers because I'm obsessing about the numbers, sorry. Okay, just giving too much. So the number is the atomic number and is the number of protons in the nucleus. Right? And then there will be an approximate equal number of neutrons. But because they do have mass, they basically double the mass of the atom. And so, but I say approximate because the neutrons can be more or less the same number of protons. And that's what we get different isotopes. So for example, you hear about carbon-12, right? Carbon-12 is actually carbon, which has 6 protons. And then the normal stable carbon has also 6 neutrons. So that's why it's 12. 6 plus 6 is 12. We refer to it as carbon-12. That's the normal isotope, the most abundant. But then there's carbon-13 and carbon-14, which are more radioactive, right? Because it has 2 more neutrons. It has carbon-14 It's radioactive and we can date it. It has a half-life. We'll get into all that later on when we talk about the fossil record, but we can actually date the fossils, the bones, because of the carbon-14 trace element that is there. And so carbon-14, it still has to have 6 protons because it's carbon, but it has 8 neutrons. Those 2 extra neutrons tend to decay, tend to come out of the nucleus, and that's the weak force, the decay. But the strong force is what's actually keeping the protons together. And it's very strong. It's incredibly strong. Consider this. Protons are positive, right? But they're stuck together. There's practically no space between the protons. How can it be? If they're both positive, they should be flying away from each other at a tremendous speed. It's like magnets. Remember how we play with magnets and we put 2 bar magnets and we keep pushing one magnet away from the other just by getting close, keeping the same. Then if we turn it around to the opposite polarities, they're going to lock in. All right. But positive and positive repel. When they're so tiny and so close, they would repel at a fantastic speed. What's keeping them together? The scientists call it the strong force. We call it mystery. Okay, so that's as far as they've gotten. Some force, thank Newton for it, F equal ma, all right? Some force is keeping those protons together so that it makes the atom stable. But when we break that force, when we break the strong force, in other words, when we split the atom, literally, the nucleus, what do we get? We get a nuclear reaction. We get an explosion. We get a nuclear explosion. And that nuclear explosion is the energy that is being released from the strong force. So back to F equal ma, no, sorry, equal mc squared, you see, that mass, when we split that mass, we get a tremendous amount of energy. Because we get the energy of the mass multiplied times the speed of light. Accelerated. Squared.
That's why Einstein was so worried about it. When he made the discovery,
Exactly.
because he said this will be
Exactly. Yes.
very bad use.
This
And
is
what
the exact. You will have life and death at your hands. It's a two-edged sword.
Dr. Jeremel, the Jew discovered the trisomy 23.
Yes.
And he said,
Exactly.
it's a big discovery, but it will be
Yes.
a problem with humanity because they are going to have
How-
trials before the
Exactly.
wounds, and they are going to
How it's
award the
used.
babies.
Yes.
And this happens in Spain, for example.
Exactly.
So
And
selection of the.
oh yeah, Scandinavia, they have actually target the unborn, the Down syndrome children, and they want to be a society where there's no Down syndrome. And so all is standard prenatal diagnosis, Down syndrome indication, automatic abortion paid by the government, and so on and so forth. And they want to limit, and they think they're doing a good thing. They truly think that they're doing a good thing to humanity by eliminating Down syndrome. But it's a chance occurrence because of the delay that women are having. They're having children in the 30s and 40s instead of the 20s when they're supposed to have them. Old eggs is the bottom line. But yeah, we'll get into all that in luxury of detail. For now, you can see that these forces are very strong. So this mass energy equivalent has a lot of power. That little formula is amazing. The power for good or evil to the point of not 1, but 2 world wars. And, you know, thanks be to God, in the Manhattan Project, we beat the Nazis to the nuclear bomb, but they were on it too. They were on it. Okay.
Father,
Yes.
okay. Biology is not my, neither chemistry is one of my stronger.
Yeah. Hey, Christina, hold on a second.
Sure.
Because I have you projected on the speaker of the classroom, there's kind of a lot of resonance. I don't know, try either speaking a little further away from your mic, or so we can see if we can hear you better. Go ahead, please. Maybe a little slower.
Can you hear me? Can you hear me better now?
Okay, let's try. Yeah, you speak a little softer now. Increase the volume. Let's try that.
How about now?
Okay. What do you-
Okay,
A little better? Yeah, go.
thank you. What I'm saying is chemistry or biology are not strong in me, but of course, I understand a little bit, but what I wanted to ask you is this atoms or these forces that we're talking about that make it stable, in order to break that, it has to be done by human made, or is something that can happen natural as well?
Yes. Okay, two ways. For splitting the atom, literally splitting the atom, we need very sophisticated equipment. All right, like colliders are called, in normal parlance, they're called colliders or particle accelerators. Individual protons are accelerated within a circle of magnets. And the magnet in front keeps pulsating and speeding up the particle. And they're sped up to, again, a humongous speed, maybe 1/3 of the speed of light or something like that. And then they are in opposite directions. And then they are guided to collide. So these colliders or particle accelerators, that proton then breaks up, explodes basically. And if there are fragments that come out, then those are the particles that make up the proton, all right? They're called particle colliders, they're extremely sophisticated equipment. I think that may be CERN. That's the tube itself where the particle goes through. So definitely machinery that is extremely sophisticated, as you can see here. All right. Yeah, this is CERN. This is the one in Switzerland that overlaps into France. So you can see, I think the diameter is about, the radius is about 15 or 16 kilometers. So they're accelerated, and it's buried several kilometers underground. That's the actual tube itself. Yeah. Yeah, it's fundamental research, it's basic research of particle physics, right? For colliders to find, they're trying to find the fundamental particle like the Higgs boson, what's making up a Higgs boson, what's making up the quarks, for example. The quarks are making up the subatomic particles, especially the protons. What's making up those quarks if they're smaller? So they're trying to find the smallest unit of matter possible, all right? So that's a very sophisticated machinery. And that's for the strong force. Again, that's what makes the atom stable, is the fact that some glue, right, that we're calling the strong force, is holding those protons together. And the neutrons also, but stronger the protons because they have a charge. But the distance can only be, from what I understand, the actual distance of the proton. So if two protons go beyond their own distance, then they fly apart. The strong force is gone. So the strong force is incredibly strong at an incredibly short distance, which is kind of the opposite of electromagnetism, but especially gravity waves, which are holding the different galaxies together on the largest scale possible. Okay, so the strong force is only strong within the diameter of the actual protons. If they go beyond that, then they fly out free. So again, it's beyond my competency to know exactly what that force is, but they just call it strong force, and they have, that's quantum physics. They have formulas, theoretical formulas for expressing it quantitatively. Okay. The neutrons, because they don't have a charge, or they have what we call a neutral charge, if you will, are easier to fly in and out. And that's what is called the weak force, in contrast. And that's also what is known as the decay. The decay is that the radioactive isotopes tend to lose neutrons over time. And losing those neutrons over time can be a matter of seconds, or hours, or days, or years, or thousands of years, or millions of years, depending on the element. Generally, the larger the element, the longer it takes for decay. So for example, uranium, which is in the 200 something, takes millions of years to decay, you know. And that's how we can tell the origin of the Earth from the trace uranium that has been left on the crust that we can study, and we study what is known as the half-life. When half of the neutrons leave that particular atom, that particular element, which is a specific amount, is the half-life. And we measure the half-life of things, material objects that have different elements, are composed by different elements. Folks, I'm getting a little too much into physics here. Don't worry about it. Basically, these fundamental forces is what's keeping the universe together. At the other end of scale, so these first two are the attractions, right? They have to do with stabilizing the atom, which is the fundamental unit or the basic unit of matter. Think about that a little bit, basic unit of matter, stable. At the opposite end of scale, at the supermicroscopic, there is electromagnetism and gravity that is maintaining the galaxies and the universe as a whole stable. So again, at this level, at this magnitude, that's why the planets are able to orbit around suns, and that suns are able to gyrate within galaxies instead of everything flying out in every chaotic direction. Right? Yes, please, go ahead.
There may be a long response, but
Don't worry about it.
what is radiation within this?
Yes, so radiation is mostly in the fields, all right? Radiation is in the fields. That's why these are fields and these other, the first two are attractions and the last two are fields. That's radiation. We can think of electromagnetic radiation. For example, if we have a cable, all right, if there's electricity going through this cable and it's linear in the direction of the cable, simultaneously at the same time, there's a magnetic field that is generated by that flow of electrons that is perpendicular and is radiating around the cable. So there are electrons that are flowing through the cable, that's the electrical part, but simultaneously there's a magnetic field that is generated around the cable radially as a cylinder that is expanding out, and of course with distance to the center, that magnetic field, that force becomes weaker and weaker, all right? So that's why it's electromagnetism, simultaneously to a flow of electrons, and perpendicular to it and radially is magnetism occurring. Now, when the field is round, is spherical instead of linear, like a cable, when it's spherical, then the radiation is literally radiating out, it's expanding literally what is called a radius, which is from a center expanding out in every possible direction. All right, and that's what is keeping our planetary system gyrating around the sun itself because of the magnetic field that the sun is generating. Gravity, somehow associated with that, but gravity is a field and it's also a wave. In my mind, again, mysterious that every body, every material body exerts gravity, exerts a pull, right? But this is not at the microscopic level, this is at the macroscopic level. So for example, this projector control and this iPhone are exerting gravity, they're pulling toward each other. But the pull is so tiny compared to the mass that is overwhelmed by the pull of the gravity of the Earth, because the largest gravity that we're experiencing on Earth is Earth's gravity, and it overwhelms every other gravity. But these two objects are pulling toward each other, all right, in a very, very weak sense. So totally opposite of the strong force, the gravitational field is the weakest force, but it's the one that is longer ranging. Is long ranging. So for example, these two books are attracting each other by gravity. Two people are gravitating literally toward each other materially because they have a material body, aside from the psychological and the spiritual stuff that may be happening. All right. every matter exerts gravity. It's just that the largest gravity that we experience on Earth is the Earth gravity that overwhelms every other gravity. Okay, and then in the solar system, the largest gravity we experience by far is also is the sun's gravity. But the planets, the other planets, the inner planets and the outer planets are also exerting gravity. For example, the Earth is exerting a gravity over the moon, and it's keeping the moon translating or gyrating around the Earth. Okay. But the moon is also affected somewhat by the sun's gravity. It's just that the Earth's gravity on the moon is much stronger than the sun's gravity on the moon. Because by mass, by comparison, the mass of the moon is much smaller than the Earth. But also the other planets, especially the large planets, the outer planets are exerting their own gravity on their own moons. I mean, Saturn, look at Saturn with all the satellite, the whole cluster of satellites that it has, okay? That is all by the gravity of this. This is not a disk. This is not an actual, LP player disc, long playing record that is around Saturn, right? These are individual, in addition to the single moons that it has. This is all dust and small particles that are so dense that they look like a disk at a distance, but it's not. You can literally go through this. The individual distance between these is discrete, all right? And one could, theoretically, if one were small enough, one could navigate in between all these millions of particles that are rotating around Saturn. So what is this? Why is this disk maintained in place? Well, it's the gravity of Saturn itself that is maintaining it in place, but rotating, gyrating around, all right? So when the large planets align, there's something about the alignment, because then those gravitational fields add up. And there is something, and for example, the water on Earth is influenced by the gravity of the moon. That's what's causing the tides. We'll get more into that later on. But the tides are being caused by the gravitational pull of the moon on the water of the Earth, the surface water. So, and that includes our water too. In fact, the female cycle of ovulation is a 28-day cycle, which is a lunar cycle. Somehow it has to do with the moon pulling on the water of the female body. And the male body is just that we don't cycle not the same way. All right, I need to move a little bit forward. Yeah, so, okay, why don't we take a little break here. We're almost halfway. I have 13 slides and we're beginning slide 6. So this will be a good time to take a little break. I've been saying a lot here in every different direction. Any particular question or comment or concern, or are you all sufficiently confused already?
I have one more question.
Please, yeah. Where are you?
So a photon, where would that
Yep.
be? Would that be also
Right.
within fields or?
Right, okay. In the words of Dr. Howard, philosopher of science, I've been listening to some tapes on Einstein. Photon has a chameleon-like quality where it depends on the spectrum. It can be seen as a radiation, as a frequency, but it could also be seen as a particle. So it has both. It has a dual nature, what we call dual nature. Okay, so as a wave or as a particle, depending if it's on the high end of the range or the low end of the range, it's going to behave more like a wave, or the high end of the range is going to behave more like a particle. Okay. So in fact, the closer it, and Einstein used the word as if it were a particle. But of course, that's on the high end of the frequency. When it starts approaching absolute zero, highest frequency, then it's behaving more and more as a particle. But of course, because we can never reach that absolute frequency, because it's theoretical, like 0 Kelvin, right? Then it's as if it would never be an actual particle because it would have to reach an absolute frequency of very infinitely large magnitude. Okay, so that's the photon, which is just a fancy name for a light particle, Just like electron is another one of the subatomic particles, right? Electrons, so you can talk about protons, neutrons, electrons, and now photons. Okay, so before we actually start getting into origin of life, again, just kind of the big picture and molecules and so forth. A little break here. Is that good? All right, so it's 11:10. How about we regroup at 11:20? Okay, so let me pause here. And remind me to restart, please. Thank you very much. So resuming recording then here, picking up on the second part. Yep. Okay. So the origins then, I mentioned that the origin of the universe, and within that universe, the origin of our planetary system, meaning our planet Earth. Then within planet Earth, the origin of life, and within the origin of life, eventually the emergence of human life. That's the phylogenetics of our species. And we'll get there, but we're going to start zeroing in on this. It's estimated that life began on Earth about just under 4 billion years ago, which was when the crust of the Earth was cool enough to hold liquid water. Again, there'll be more details about this and actual images and so forth when we get to the environmental bioethics course. And we'll look at the formation of our planetary system by a process known as accretion. Accretion, don't worry about it, we'll get there, What I want to do is, with regards to life, and I'm just putting the 4 billion years out there as a point of reference, okay, that basically there's been quite a bit of time, 4 times 10 to the 9 years for evolution to occur from a single cell that we call a protobiont. Again, don't worry about the term, we'll look at it in further lectures on this course. The protobiont would be a precursor to an actual living cell on Earth, and how we can get there from inorganic material. For now, I just want to give you basically more vocabulary, which are these organic molecules, right? So basically all molecules on Earth can be subdivided, subgrouped into organic or inorganic molecules. And the organic molecules are the ones that make up for life. And that's what we talk about, organic life. So pretty much, unless I specify otherwise, when I talk about life in this course and in this program, I'm talking about real, physical, organic, biochemical life. I'm not talking about the life of the angels, the life of God, or even our spiritual life necessarily, right? I'm talking about physiological, organic life. And that life is essentially a very ordered process of chemical reactions, multiple myriads of chemical reactions that we call overall metabolism or body functioning. Metabolism can be at the level of the whole body, the organism, whatever organism we're talking about the human, we're talking about a giraffe, or we're talking about an oak tree, all right, because plants also metabolize, of course, or fungi. Or, so that's at the level of the entire organism. Or we can also talk about metabolism at the level of the cell, cellular metabolism within the cell, because the cell is the basic unit of life. Not the basic unit of matter, because the basic unit of matter is the atom. We have different scales here, right? Different orders of magnitude. So the basic unit of matter is the atom. But there's a lot of matter that is inorganic, that is not living, and it's made up of atoms. But the basic unit of life, okay, in other words, the smallest living thing is going to be the cell, what we call a cell. C-E-L-L. And the cells is made up, what makes up a cell? Well, the cell is made up of macromolecules. These 4 organic molecules, 4 groups or 4 types of organic molecules. Before we look at the actual groups of them that we hear all the time, you know, the carbs, carbohydrates, lipids, proteins, nucleic acids. I want to mention that for a molecule to be organic, all right, it needs to have carbon and hydrogen, carbon and hydrogen. So for example, H2O, what is H2O? Water, right? Water, H2O, has oxygen and has hydrogen, but doesn't have any carbon. So water, even though water is the basis for organic life on Earth, water itself is not an organic molecule. It's inorganic. Okay. Another example, CO2. CO2 is carbon dioxide, right? Carbon dioxide, CO2. So it's got carbon and it also has oxygen, but it doesn't have any hydrogen. So CO2, even though it's produced by living things, by metabolism, by respiration, we produce CO2 and all living things produce CO2, even plants produce CO2, fungi, everything, yet it's not an organic molecule. So CO2 is inorganic because it lacks hydrogen. Water lacks carbon. So for it to be an organic molecule, it has to have carbon and hydrogen together. And the basic pattern is that the carbon is going to be the skeleton, the core of the molecule, and the hydrogen is going to coat the molecule to stabilize the atoms in that molecule. By the way, again, just very, very basic knowledge here, molecules are made up of atoms, okay? Now, there can be small atoms, like small molecules, like H2O, which has 3 atoms, right? 2 of hydrogen, 1 of oxygen, or CO2 that has 2 carbons and 1 oxygen. Just small molecules, I'm talking about molecules as a whole. Or it can be huge molecules like DNA, which has millions, billions of atoms. Single molecule. The molecules come in all sizes and shapes, but it's all on how many atoms forms that molecule. And for those molecules to be organic molecules, they need both carbon and hydrogen. Typically, the carbon forms the skeleton, the core, and the hydrogen coats the molecule to stabilize all the valences, technical term. All right, so let's get into these 4 types of organic molecules. Again, we're building a basic vocabulary here. Carbohydrates, so they have carbon and hydrogen, like sugars and starches are carbohydrates. Then lipids, it's just a fancy word for waxes, oils, fats, greases, anything that doesn't readily mix in water, doesn't dissolve in water. Typically, they're lipids. Okay, so lipids are the fats, oils, waxes, greases, all that. Then we got proteins. And proteins are made up of subunits called amino acids. There are 20 amino acids that occur naturally in nature, right? The essential is known as the essential amino acids, natural amino acids. They make up proteins. Proteins, I can tell you, are the ones that do most of the work in the cell. There are thousands of different proteins. For example, enzymes are proteins. Okay? And they do mostly the work. They are the workhorses of the cell. Proteins, many different types of proteins. And finally, nucleic acids. So this is the category that most people are least familiar with, nucleic acids. And they're just called nucleic acids, first of all, because they are in the nucleus of the cell, right? And secondly, because, well, they have an acidic composition. They're on the low end of the pH scale. It's just a technical thing. But they are known as DNA or RNA. DNA and RNA, again, we'll look at these molecules more in detail as we go further in the course, but these are the ones that make up the nucleic acids. And so these are the 4 basic types of organic molecules, just like we have 4 fundamental forces in physics. We have 4 groups of organic molecules in biology, biochemistry, and medicine, and all this. Together, all these are called macromolecules because they're made up of typically dozens, hundreds, or thousands, or millions of atoms, but from dozens up. The sugars are kind of the smallest ones. They're made up of dozens of atoms, like glucose, for example, C6, H12O6, so that's 24 atoms. That's kind of the smallest ones. Amino acids also, a few dozen atoms. To the largest ones, which will be DNA and RNA in the billions of atoms, right? Single molecule. The others, mostly lipids and proteins, are in the mid-range, typically thousands of atoms, hundreds of thousands. So that's why they're called macro, because they're large, even though we cannot see them by the naked eye, but some microscopes, very sophisticated, are beginning to image these molecules. All right, still some basic concepts here, that life on Earth exists because we have liquid water, and this is the range of liquid water. We have the 3 states of mass, gas, liquid, and solid, right? And we can go from one state of matter to another by increasing or decreasing the temperature. So if I take water, what I normally call water is liquid water, and I put it in the freezer, it will freeze and it will become solid water, which we call ice, right? It's the same H2O molecule, but now it's crystallized. It's from a crystalline structure, so it's solid. On the other hand, if I take that water and boil it, it becomes steam, or what we know as water vapor. And then that water vapor, the molecules of gas don't hold their own shape. They disperse. They take up essentially the volume of the container. Those are the gas laws, that they take up the volume of whatever container they're in. And the range is 0 to 100 degrees centigrade or Celsius for liquid water, all right? But even at the extreme, it's already getting very difficult for life. So life close to 0 degrees centigrade is very difficult. Life close to 100 degrees centigrade, again, is extremely difficult. Think of like the mid-range here. For us, the normal temperature, our body temperature, internal body temperature is 98.6. You say, well, that's very close to 100. Yeah, but that's in Fahrenheit. That's not in centigrade. In Celsius is, you know what Celsius is for body temperature? 36, yeah, between 32 and 36.5, right? 36. So you notice that the range is kind of on the low side, 36. 36 is comfortable, and that's internal temperature. Okay. So anyway, this is what makes for liquid water, which makes for the possibility of organic life, because organic life biochemically is a bunch of chemical reactions occurring in an orderly fashion, what we call cascades, orderly fashion, from one reaction to another to eventually end up with a product that does something in the body. And metabolism is a fancy word for life, or organic life. So we need to look at the primitive atmosphere, which was what we call inhospitable. Inhospitable means it was nasty for life. There was no real possibility of life as we know it today. If we were to go into this primitive atmosphere, we would just intoxicate within a few minutes and die, all right? And so this primitive atmosphere of the Earth, going back to about 4 billion years ago, between 4.5 to 4 billion years ago, even as the water was becoming liquid, that was necessary but not sufficient. The primitive atmosphere also had to change the gas component of the Earth, right? The atmosphere had to change significantly for allowing life to flourish. And it's estimated actually that the atmosphere has changed dramatically about 4 times. But the first 3 times were fairly ancient. the first few million years. Eventually, when a group of organisms established on Earth, on the surface of the Earth, they changed the primitive atmosphere drastically to what we have today, which is basically we would call a benevolent atmosphere. Specifically has sufficient amount of oxygen, O2, about 16% of O2, that is breathable and that is necessary for metabolism. So that percentage of oxygen is a significant one. It was made mostly by some very, very primitive organisms known as cyanobacteria. Cyanobacteria that can photosynthesize. And this happened fairly early on, around 3.8, 3.9 billion years ago, billions. All right, so that allowed for a benevolent atmosphere. That was one change. The other change also is that in doing that, especially the ammonia and the methane and the hydrogen and the CO2, the last three became significantly reduced and replaced kind of by another gas that is inert. And that gas is nitrogen, nitrogen N2, because these are molecules that stabilize each other. So just like we have oxygen O2, nitrogen is N2, is stable. It's known as diatomic nitrogen, a gas in room temperature or in ambient temperature and ambient pressure. Nitrogen is what we call inert gas. Inert means that it goes in and out of our lungs and doesn't do anything at ambient temperature and pressure, okay? What we call STP, standard temperature and pressure. Under pressure, on the high pressure, nitrogen can actually work its way in through the lungs into the circulatory system, and then it's a danger. And that happens when, for example, in scuba diving, where we have the atmospheric, we have the pressure of the water column on top of the diver that is compressing the gases. So the diver is breathing compressed gas from the tanks. And so compressed nitrogen can be a problem, can cause bubbles of air inside of bubbles of gas, embolisms, and can form clots. But under ambient, normal, natural pressure and temperature, nitrogen gas is inert. It goes in and out of our system and does nothing, thanks be to God, because that's about 70% of the atmosphere. Okay, so we're breathing mostly gas, nitrogen. All right, so that's what we call the benevolent atmosphere, very, very different from the primitive atmosphere that had to be changed by these cyanobacteria. Now, none of this was done directionally, all right? It's not that the cyanobacteria all of a sudden got together one day and said, okay, folks, we're gonna change the atmosphere so that a few million years from now, we can have Homo sapiens arise on the evolutionary scale. No, no. This is chance occurrence, and at the basic bottom line of it is going to be chance mutations that happen to favor the survival of that particular organism. But it all begins with chance mutations, okay? So again, we review the whole issue of the species because we're going to want to focus eventually on the human species. Remember that biologically, we're using the biological definition of species, in other words, Meyer's definition of species, which has to have two characteristics. Organisms that can interbreed, that they actually recognize each other, individuals that can recognize each other. And they're going to recognize each other how? By using mostly five things that we spoke about, that I spoke about at the beginning of the lecture. The senses, the external senses, either by sight or smell or tact, touch or licking. So sometimes several senses are involved in that recognition of each other, of the individuals, and they're in their brains. The kinesthetic sense is saying internally, oh yes, that's another like myself, so we can mate. It's another like myself, okay? So other species will recognize each other that way. Necessary but not sufficient. The second component is that the product of that mating, of that interbreeding, is a fertile offspring. So it's an offspring that looks like them and metabolizes like the parents, but can also has the capacity, potential for interbreeding also. In other words, for recognizing another one like self and mating. Whether the actual mating occurs or not, that's a whole different question, okay? But at least the potential. In other words, that the offspring are fertile. They have the capacity for reproducing. And then you can see with that second condition or provision, then that's a perpetuation of the species, because those offspring of the children should also be fertile or being of the same species. So that's the next generation. So those will be the grandchildren, and then the great-grandchildren and the great-great-grandchildren, as long as they are capable of identifying each other as breedable and produce offspring that are fertile, then the species is perpetuated or continued. And so in genetics, the first first mating that actually occurs is called the P generation for parental generation. So our parents, whether they're mother or father, they are the P generation for our perspective. If we interbreed, and then the first children, the first generation of children is called the F1 filial, F for filial, which is mean hijo, like sale filio, hijo is son or daughter, right? Son or daughter, that's the filial generation, F1 for the first. And then the children of the children is the F2. And the children of the children of the children is the F3. And that's what Mendel was doing. Mendel started with parental P's, all right? So P, male and female, PP, and then he made it those, he bred them, bred them, and then he got an F1 generation. And then he interbred the F1 generation and got an F2, an F3, and that's how he was following the progenies, and that's how he got his ratios. Question, comment.
Life does not necessarily mean it has to be a species. What I'm getting at is.
No, very good point. It does, because that's another point that I make that specifically in the beginning of life course, just coming up in May, after this one, when we look at bioethical issues at the beginning of human life. One of the arguments that I use, and it's a philosophical, you see that I'm kind of shifting back and forth between philosophy, biology, and theology, right? Drifting back and forth, but that's the integral picture, that's the bigger picture. And it has to be of a particular species. In other words, when we walk out these doors into nature, any nature, and including not just on land, but even in the ocean, whenever we find a living organism, it's of a particular species. There's no unspecific life that we know of on Earth. There's no unspecific life. There's no just a living mass of tissue that or cells that are clustered together that doesn't belong to a particular species. And what is defining it is the DNA, the genetic, the inheritance molecule. That's what, and that's what that at the same time that makes for the consistency. So the progeny of that mass of cells that reproduces somehow is going to be like itself, because the DNA maintains it within the same species. Now, they don't know. A lizard that's walking by right now doesn't have a clue that it's a lizard, all right? We do. They just live by instinct. That's why we, Aristotle, we have access to lizard nests. And it's not a palm tree, all right? But we also have access to palm nests. We know what a palm group is, all right? And so we have access to the essence of things. They, as far as we can tell, don't, but they are essences. So what we say philosophically, an essence, biologically is a species. And grammatically is a what? It's a noun or a substantive. You see? Exactly. So we are developing also an ecumenical, if you will, an ecumenical vocabulary where we can go from biology species, grammatically noun, substantive, and philosophically the essence of things, the quid est, the what is it. So bottom line, there is no unspecific life on Earth. And that is proven experimentally, all right? That's not a theoretical argument. That is that whenever we have discovered life, organic life with the four with macromolecules, okay, it's always of a particular species. And when those individuals reproduce, they produce more of the same. And a palm tree will never, will never, no, we can never say will never, but a palm tree that we have studied over decades and centuries has never produced a lizard. It may produce variation, and that's where Darwin sneaks in with variations. Okay, what palm tree are you talking about? Because are you talking about a sable palm, or are you talking about a fishtail palm, or are you talking about an areca palm? Now we got variations. Okay, and so what Darwin had, he was challenged by calling different animals and plants and fungi species. He liked to call them varieties. But there's a fine line, but a real line between a variety and a species, because a variety is still within the same species. Take dogs. We call them breeds, right? Breeds of dogs, but they're all the same dog. And so they're all Canis lupus familiaris, all right? So hypothetically, if a Chihuahua and a Great Dane could figure out how to mate, they would produce offspring that in principle are fertile. Yes, but they're all the same species. So we don't have unspecific life on Earth, and therefore that argument of, oh no, it's just a little mass of cells inside of you growing inside, doesn't cut it. Doesn't cut it biologically. Biologically, scientifically, with the actual objective facts, independent of my opinion. So again, within the big picture of the time sequence, when we're going to talk about the evolution of the human species, all right, we can back out a little bit and talk about the evolution of the genus Homo. And we can start even backing out a little bit further. Remember how I gave you the Linnaean classification from the most specific to the most broad, the most specific being the species, the most broad category being the domain. All right, and we went species, genus, several species form a genus, several genera form a family, several families form an order, several orders form a class, several classes form a phylum, several phyla form a domain. Those are all the categories. Okay, it happens that, of course, we scientists, we don't like people to understand us, so a simple picture we need to complicate and make subdivisions. So we talk about sub and supra categories, sub and supra. So there will be a subphylum before there is a supra class, and so on and so forth. All right, so we start splitting them into finer details, because this classification is imposed. It's artificial in the sense that we are creating a classification system simply to have a language, to have a taxonomy, so that we can talk about, well, what organism are we talking about? All right, and in what family does it fall, what group, and how is it similar or different to other organisms? Do they have hair? Well, then, and mammary glands go together, then they're mammals, as opposed to reptiles who have scales, as opposed to hair and so forth. But a scale is, or a feather, for example, a feather is a super sophisticated scale. And so now the tendency is to group birds and reptiles together, because a feather, which is made out of keratin, which is a protein, which is also the hair is made up of. Okay, so we have common ancestors there. I digress. What I wanted to say was that earlier, yes, oh yes, the categories supra and sub, don't worry too much about it, except for one, that is the tribe. And the tribe doesn't apply everywhere, but a tribe applies quite a bit in mammals. And it's between genus and family. It's wedged in between genus and family. Okay, so we are the Homo genus, two words, the genus Homo. right? Like as in Homo sapiens, our biological last name, which unites all humans into one species and one population throughout the world. But we talk about the human family, but that is colloquial language, is technically is not really proper, because at the level of family, we are a primate family, which includes also the gorillas, the orangutans, the chimpanzees. So at the level of family, we have other distant cousins that are not human, but are primates. Okay. So this category of tribe is very convenient because we wedge it in between genus and family. And so we can talk about the hominin, notice the language, the hominin tribe, right? Which will separate us from the Gorilini tribe. Gorilini tribe is the gorillas. Or the Panini tribe, which is a pan-troglodytes, which is just a fancy word for chimpanzee. So we got the Gorilini family tribe, and we got the Panini tribe. All right, so we just got saved by the nomenclature to not be in the same tribe as those other very distant cousins. All right. But that tribe, the divergence of tribe, estimated to have occurred about 8 million years ago. Then, between hominini and panini, about 6 million years ago. So the divergence with the chimp of today, pan-troglodytes, happened estimated about 6 million years ago. Give or take 1 million on either side of buffer. So actually between 5 or 7 million years ago is the range. The genus, now in the genus, okay, about 3 million years ago. Because there are other hominins that are not chimps, but are not Homo. They are the Australopithecines. Australopithecus, again, you'll come across the actual name further down, but the Australopithecines are the southern apes. You've heard the name Lucy. She was the famous one that was discovered erect, the fossil record, of course, but they found first by the prints on the mud, which is also considered a fossil. So an imprint can also be a fossil, all right? But the imprint is bipedal, and it goes on and on and on and on. So obviously she is bipedal, right? Standing erect already, upright, and not doing the knuckle walking of like chimpanzees do. That they can walk upright for a while, but eventually their spine, because the spine doesn't have an S, has a C, then they have to come down on the knuckles eventually because they get tired out. Okay, but no, Lucy was walking, right? And she had a little kid with her because there are other set of footprints next to her. And then eventually they discovered the skeletons and they start putting the skeletons together. She was maybe half our size, but she was already bipedal. But she was not Homo, she was Australopithecine. In other words, she was a southern ape. And the brain capacity, that's the key one. The brain capacity was maybe 1/2 or 1/3 of our brain capacity. And that happened about 3 million years ago. We speed it up all the way to modern man as we know each other today, about 200,000 years ago. Okay, YA years ago, about 200,000 years ago. The actual range here, it has to do between what we call physiologically modern human or anatomically modern human and culturally modern human. Okay, remember the Flintstones? Okay, the Flintstones is a caricature of what would be anatomical modern humans. But they went around in barely little strips of clothing and still living in caves and harnessing fire and so forth. They didn't have culture, meaning they didn't have significantly written language or tools or very primitive tools. okay, but very primitive technology. They really didn't have culture as such, material culture, not living behind actual buildings or structures or that, what's called material culture, anthropologically speaking, about 200,000 years ago. So we're a very, very recent species that has arrived, has arisen on this planet.
Well, the Neanderthal would be considered modern man.
No, but we did coexist with Neanderthal. They are actually Homo neanderthalis. And that's why we need to talk about Homo at the genus level, because there were other Homo that were not sapiens, like Heidelbergensis and Neanderthalis and Homo habilis and Homo faber and all these. All we have is a fossil record. But Neanderthal was the most recent one, the one that lasted the longest. And we coincided in Europe as recently as about 40,000 years ago. So it goes way into this. You know, we coexisted with Neanderthals, and there is some interbreeding. So if you do that, what do you do online? Ancestry.com and 24andMe. What is the little thing? Me and 20. Anyway, if you do your ancestry, you'll come up with a small percentage of Neanderthal DNA, and it's there. Okay, it's there. So we interbred before we wiped them out. We made it with them. Well, our ancestors did. So here's an example of at least half a dozen other Homo genus that are not sapiens species. And none of them are living today, as far as we know. We have not discovered any of these alive, okay? But we do have the fossil record. And if we have fossil record, then we can date them by carbon-14 mostly, and find out when they were alive, because if the bone is there, then that bone had flesh and guts at some point and was walking around. Okay? So these are some of the...
Father Trophy.
Yes. Mm-hmm.
So I'm not even sure what is my question, but it has to do with God.
Yeah. God. Where is God?
So, well,
You know,
okay, so he is the creator of everything.
Yeah.
We know that, that's a given, we understand that, I don't have a problem with that. But then what we're really saying theologically is that it was only until probably 200,000 years ago that God started communicating then with us, because that's the species that started. I mean, I have a little, I don't even know how the question is, but.
Exactly. Very good. So you're already struggling with what we're going to be covered for the next 3 or 4 months until we get to
okay.
Absolutely.
Well,
that's the thing. In other words,
okay.
short answer is that evolution can give us and has given us the material being anatomically and physiologically. What evolution cannot give us is a soul or a conscience in the spiritual sense. And that's what we have that's where we have direct intervention of God, okay? But we have to posit it as a hypothesis, because we cannot weigh the soul or measure it in empirical terms. So it's outside of realm of science, but it's squarely within this realm of faith. And that's what we have to do, science and faith together, to come at the full picture of the human, all right? But evolution has given us a material body. And that's where it's my last slide, between matter and form, and we'll get into, okay? So there's a little saying in Italian when we are having an intellectual discussion, right? At some point, one of the persons will raise the question, in che senso, in what sense do you mean that? Directly or indirectly? For example, Jesus Christ, you're a catechist. Jesus Christ instituted all 7 sacraments. So as far as we know, he never baptized anyone. Well, there's actually a little reference that Jesus was also baptizing together with John the Baptist, but it could be a corruption in the text. We don't know. But he never married anyone that we know of sacramentally. You know, he did forgive, and he forgave sins, so it was a sacramental forgiveness, and so on and so forth. So he did establish all 7 sacraments, and he certainly, as far as we know, never anointed anyone with the anointing with the oil of the anointing. He did anoint someone with saliva and earth and soil, mud, but as far as we know, not with consecrated oil, consecrated by a bishop, one of his 12 apostles. So what I'm trying to say is that he instituted all 7 sacraments. Some he did directly, and others he did indirectly through the church, which is the body of Christ. Okay, so in qué senso, in what sense does God intervene, and in what sense does God create? So he creates directly and indirectly. So indirectly, he creates by establishing the laws. So we can say, yes, evolution does happen, but who created evolution? In other words, the laws by which evolution have to work, because evolution is a mechanical thing, someone had to establish those laws. All right, and that's why I talk about the fundamental forces and things like that, try to go a little bit on the basic side. Even the DNA. So I told you a little, I'm giving you punchlines already, I'm giving you the end result kind of prematurely. The mechanism of evolution, I'm saying, is genetics. And what's the basis of genetics? Precisely the DNA molecule, the molecule of inheritance. That molecule of inheritance follows a molecular structure that is very compact, very succinct, very stable, with billions of atoms. And what's keeping that molecule stable? Well, the molecular forces of the atom. So we go into the strong force for the nucleus, the weak force for the decay, right? And so one way or another, who established the 4 fundamental forces? Who establishes the basic laws of the universe? The basic fundamental laws of the universe. It could have been a different universe, okay? And so those laws, we believe, were established by God. But how do we prove that? Well, we can't, because it's not empirical. It goes beyond the scientific, and that we go into the metaphysics. So we got physics that we can measure, and then we got metaphysics, like the word itself says, meta is beyond. By definition, the metaphysics is beyond, but is no less real than the physics. So for example, no normal, sane human being doubts that we have a body and we all have bodies, okay? But how about the friendship, the love, the connection, the empathy, or even the fear or the anger that we feel between each other? It's unmeasurable. How much does love weigh, right? How much does generosity, not in terms of dollars and cents or act of charity, but the actual sense, the feeling, right? The sentiment of empathy and so forth. Well, those are metaphysical realities. Okay? Just like mathematics, really, mathematics itself is metaphysical. Again, going back to triangle. Triangle, where's the triangle? The triangle is in our minds. It's an abstract thought. But how much does that thought weigh? No. So there are metaphysical realities that are as real as the physical realities. But they need a certain level of faith in order to maintain them. Right? So that's why I'm saying science and faith have to work together. It can't be all scientific, because then we're leaving out part of the picture, the God image picture. It can't be all theological and spiritual, because we are in an organic body. That's the whole point of John Paul II. Body and one, body and soul one. The whole theology of the body is body and soul one. Okay, so anyway, you prompted me to get to the last slide. Characteristics of the Homo lineage, right? You can see here, and we share this with all these other guys here, okay? As far as we have found in the caves with remnants of fire, campfire, and also that it's not a wildfire, but it's a campfire, in other words, harnessing fire, and also the tools and the tool making, the rock that made the stone that made the other stone, so the hammer that made the knife in stone, etc., and also some remnants of their clothing. These are all characteristics of the lineage of the Homo, but go beyond the sapiens. The only thing is that the other non-sapiens Homos are not around any longer. They're extinct, okay? But we have whatever they left behind, including their bones. Now, as far as the soul is concerned here, what's this? Oh, this is Meyer. Okay. So, see, when we start talking about symbolic culture, like Altamira, for example, or Lascaux, which are the caves in Europe, primitive, that have art on the walls. I'm sure you've seen these images around sometimes, right? Whether they're hands that powdered on the wall, a negative, this like called a negative impression, and this other one is a positive impression. Actually, painting may have some ritualistic, symbolic, metaphysical belief to them. So this primitive art could actually be religious art, trying to harness and capture the essence of the animal that they were trying to hunt. It's not known. It's very very puzzling. This distance actually has been enlarged. This is a reproduction of the Altamira cave in Spain, but the actual distance is much smaller. It's like 2 or 3 feet. So actually, to see this upside down, one has to be laying on the floor. I had the privilege once when we were little kids, my brother and I, we were in Altamira, the original cave. Now it's closed to the public, but we crawled in there 3 or 4 feet watching the original thing. Like I say, this is a very precise reproduction of it. And the paintings are super huge at that scale, you know, and you don't really get a perspective on it. So I had to, and there's so many of them, and to crawl into that space. So it has all the feel of a ritual that is going on, okay? And what today we call religion.
It's from what time?
40 to 50,000 years ago, more or less. The one in France is another famous one. It's called Lascaux. We'll look at them also in more detail, but just so that you get a little taste. Similar, look at that, but a very different part of, well, it's still continental Europe. So these are certainly nomads that are walking around in caves, establishing in caves, but this is sapiens. This is definitely Homo sapiens. Okay, now some of these are from Australia and I think New Zealand and so forth. So it's a different continent altogether. It's a different hemisphere. It's a southern hemisphere, and yet similar pattern. Independently arising or semi-independent in that there's a common origin, but different clans. That's another category, clan, all right, which is within the genus Homo. It looks like here the hunting turned around. But anyway, just giving you a foretaste of what we're going to get into more deeply. I want to talk about this one for a moment, in the next few minutes that we have around, because Christina gave me a segue into also. Matter and form. There is a dictum in science that we say form follows function. However, that form, let me make this right or grammatically correct. The dictum is form follows function. However, form itself, I'm putting in quotations, because when we scientists, empirical scientists, natural scientists, obsess about measuring and getting quantities, right? I talk about form. Form follows function means that the structure of the thing is according to the function of the thing and not vice versa. For example, the arm. If my hand is supposed to reach my mouth, like for feeding, and my hand is at the end of the arm, at one end of the arm, and my mouth is at the other end of the arm, then the arm better have a hinge somewhere so that my hand can reach my mouth. Otherwise, if there's no hinge on the arm, then my hand is never going to reach my mouth. All right, so the structure of the thing, the structure of the arm is according to the function of the thing, which is to enable, what's the function of the arm? Well, one basic function of the arm is to enable my hand to reach my mouth so I can feed myself. So that hinge we call the elbow. or the elbow, and the other one is the, what's this thing? The shoulder. All right, so elbow and shoulder are the two functions of the structure, right? So form follows function means that the structure of the thing is according to the function of the thing and not vice versa. Okay? Form follows function. It's a basic dictum. However, form in the empirical sense actually means shape. The shape of the thing is according to the function of the thing. The structure, the actual bone structure, and then all the surrounding ligaments and other parts that allow me to move it, like skeletal muscle and so forth. Philosophically, we make a distinction between, so let me say this. In parentheses. When we scientists talk about form follows function, it's nice because it rhymes, the 3 F's, you know, it's nice and pretty. But we actually mean shape follows function. Philosophically, now we're going to talk as philosophers and theologians, because philosophy is the tool of theology. Okay, we make a distinction between form and shape, and it really is actually very simple to prove. We have right now between the virtual students and the physical real present students here, or bodies, all right, we have what, 4 of you are virtual right now and 3 of us are here, so we have 7 bodies, human bodies, right? So, and how many shapes, or how many human shapes do we have? We have 7 human shapes, because as far as I know, none of us are identical twins, or we'd be looking exactly like each other. And none of us look exactly like each other, even without the clothing, all right? So we have 7 shapes. We have 7 human shapes between the virtuals and the physicals, right? Or the in-presence. So 7 human shapes. Anyone disagree with that? Get my point? All right. How many human forms do we have among the 7 of us? It's a philosophical question, and it's also a theological question. I hope that you'll agree that we have one human form, one human species, one human essence. We're all human, in other words. The fact that we have different shapes doesn't make us more or less human. It just makes us different shapes by the actual shape, you know, by the structure. But we have one human form because we are one human species, biologically speaking. We are one human noun, grammatically speaking, substantively, right? The substantive is man, woman. Even woman is of man because the W-O is Old English for of. So woman is of man. So man, like Adam, right, is the human. Human comes from man. It's just man is a shorthand for human. Okay, so we're all human. One species biologically, one noun grammatically, one substance, one essence philosophically / theologically. We're all God's image, regardless of our shape. Regardless of the shape that we have, as long as we're human, we're God's image. Regardless of the shape, regardless of the age, regardless of the merit or dismerit of our personal lives, whether we are the greatest saint on earth or the lowest scum villain that we can think of, okay? We are God's image. So John Paul II is God's image, and Adolf Hitler is also God's image, in spite of themselves. Because we're one humanity, we're one form. Philosophically, we talk about form. Theologically, we talk about image and likeness. So there's a consistency, okay? And that's why also I love just the simple biological definition of species, because we can segue into language, which is culture, meaning the noun. We got proper noun and common noun. And then we have philosophically / theologically, the metaphysical language of form or image. And there is a consistent, as far as I can tell anyway, we can make that lateral transition, if you will, back and forth. Okay, and now we can establish a common language between priests, medical doctors, and catechists, and other people in general, because one of these languages is common to all of us. So matter is the material stuff that empiricists can measure, and form is that of which philosophers and theologians can talk about. And we are what we call a substantial unity of matter and form together. Evolution through genetics has given us our matter, our proper matter. In other words, Homo sapiens, the DNA, the human DNA that expresses in our bodies. But what evolution could never give us, what our parents could never give us, the most that our parents gave us was 2 cells, an egg and a sperm. In other words, the package of the DNA. What our parents could never give us, as much as they could try, is a soul. Because that is the prerogative of God, and that is the direct, immediate prerogative of God, and exclusive. And that's what makes him omnipotent, capable of creating a new soul that has never existed before, will never exist again, and it has an origin, but has no end, as in end destruction, will continue for all eternity. Okay? An eternity, according to our beliefs, of salvation or damnation, but eternity. And then the big question becomes, in that system, what about identical twins? What we call monozygotic or homozygous twins. Homozygous twins, that they are identical, not fraternal twins, coming from 2 eggs that were ovulated simultaneously and were fertilized by 2 sperm, because there are millions of sperms hanging around, okay? But a single egg fertilized by a single sperm, which within the first 2 weeks of human embryonic development split into 2 or more identical twins, and then grew, and they're walking around, and they're the same sex or gender, because they come from the same sperm, which determines the sex/gender of the human and mammals. But they're 2 individuals that have their own soul. They don't share a soul, and they don't have half a soul either. They have a full soul, where it's created individually, independent by God. So how can that be? And that's the question I'll leave you. How can that be, fathers, priests, of the soul, which one of the characteristics of the soul, aside from being individual and personal, is indivisible. Indivisible, not divisible. We cannot take a knife and cut the soul in half. So how can identical twins, how can we justify still the beginning of life at fertilization, when we still within the first 2 weeks of embryonic chronology, we can end up with identical siblings, 2 or more, right? And still maintain the possibility of each one having their own individual soul. We get there.
Question on the use of theological use of the word form then.
Yes.
Can we, under circumstance, use the word form to indicate the individual human soul and the collective human species soul, or Homo sapiens soul?
Yes on the first one and no on the second one. Okay, first of all, a little clarification. Remember Aquinas, seldom, never deny, seldom affirm, and always distinguish. Okay, so the first distinction is that form is more philosophical than theological. For theology, we'll go more into image and so forth, but soul, form is squarely a philosophical term. Also because we can talk about form with secular philosophers. You see? So that's the clarification. Beyond that, you mentioned that the human soul at the individual level, fine, no problem there. We're talking ontogenetically. But the human soul, the level of species, we would have difficulty because, again, the soul is individual, personal, and indivisible, whereas the human species is a collective, it's a population. All right. Now, if you want to trace it to the origin, now we're talking phylogenetics, and the first human sapiens, whom we call, theologically, we call them Adam and Eve. Biologically, we call them mitochondrial Eve and Y chromosome Adam. There's a parallel, even though they're not exactly the same, but they're analogous languages that we can use, okay? But collectively for the species, we cannot talk about the soul of a species because as a group, as a population level, because there are X number of individuals in that population. And each one of those individuals has his or her own soul, okay? If you take it to the origin, yes, the first group or the first parents. But even the first parents, we have to be a little careful because biologically, several individuals that are close within the same clan genetically can be considered a single species. It can be considered a single individual genetically because there's no more variation, there's no more diversity. So I understand, for example, the cheetahs in Africa have become so few, maybe there's a few hundred left, that genetically they're as if it was a single individual. There's not enough variation within them. I'm just talking biologically, all right? So when we talk about Adam and Eve, Y mitochondrial Eve and Y chromosome Adam, it doesn't necessarily mean one male and one female. It could have been several females and several males, but they had essentially no variation between them, right? Genetically speaking, originally. Time had to elapse for chance mutations to occur and begin to establish variations, all right? And so those are the varieties of Darwin that may or may not lead to speciation, to an actual distinct species, where the individuals, even though they look alike, they don't actually recognize each other as the same, and so they don't mate. And even though they look very similar, they actually don't mate because they don't smell just right or something like that. Or they're not actually behaving just the same way as our group over here, all right? So I'm giving roundabout answers, but yes, the individual form at the individual level of each person, but no at the level of species as far as the soul is concerned. So if you want to equate form to soul, then we have to stop at the individual level. We cannot go into the population level. We all have a human soul, but we have each one of our souls is individual, is unique.
So from that perspective, then it would be one form philosophically in this class.
Yes.
But our souls will never be one form. It will be
Exactly. They're individual. It's the human form philosophically, but we have individual, personal, and that's the individual creation of God right there. Okay, so I think that's Christina's question or comment. That's the direct, immediate intervention of God and exclusive that no one else can do. And for whatever reason, he did not will to do that even with the closest relatives. Now, again, the big question, and I'm jumping to the conclusions of the course here, maybe we can take a break after February, reuniting May, giving you the intermediate parts, is did Neanderthal have a soul? We don't know. We could speculate indirectly by some of the, where is it? By some of the characteristics, perhaps, maybe. In other words, we have to get, again, giving you a little insight, the moral or ethical quality. So one of the qualities of the soul or the conscience is an ethical conscience. The conscience, I'll talk more in depth about the conscience, but the conscience is like a crystal. It has different shapes, you know. There's a social conscience, there's an intellectual conscience, there's an ethical, moral conscience, okay? And there's an artistic, aesthetic conscience. All are different aspects of the same reality that the conscience, right? The substance, the noun, but the adjective is different aspects of that consciousness. My opinion and my insight is that we may be able to get at the ethical conscience of some of these guys, of which we only have bones and material culture left behind, precisely by what they left behind and what did they not leave behind, ethically. So in other words, did they exhibit, possibly, could we safely assume that they exhibited ethical behavior, or were they living strictly at the level of instinct? That to me is the difference between a human soul and a non-human soul. In fact, Aquinas, going back 800 years, with a very defective biology, horrible biology, because of the biology of the time, still talked about the human soul, the animal soul, and the vegetable soul. Okay? And only the human is eternal. The other souls is what we would say basically we call instinct, and in the plant, just metabolism, being alive, right? But he called it soul, or because the Latin for soul is anima or animus, which is being animated, that they're alive. Okay, so that equates with basically life, organic life. But the human, beyond the organic life, there's also this supernatural or metaphysical reality of eternity. Okay, folks. Again, we're in the introduction. I've been a little all over the place, but I hope you kind of get the picture more or less. And I just want to leave you more confused at the end than we started with.
It was more confused, but it's fascinating.
Yeah, so you see, the more, because the more we answer questions, the further questions arise. And there's another analogy there that will run before over time now.
I will try to do a kind of a making sense summary. We'll see what happens.
Yeah. Review the video and look at the, if you're not sufficiently confused, go over the video again and go over the PowerPoint, and then I can guarantee you, you'll be sufficiently confused for next Saturday. Okay, thanks a lot. Let me just magnify the tile here in case there's any question, comment. People are good. You were able to hear, hopefully, at least some of it. And I'll post this, just like I did last time. You were able to access the video and the PowerPoint and stuff. So far, so good? Okay, let me know if there are any issues, all right? Okay, so let me stop the recording now so that we can finish this part. Okay.